our review session concerning chapter 1, which is single and three-phase circuits. However, in this part, we are going to focus on the three-phase system. Okay. So the points in this part, we have the advantages of three-phase system over single-phase, three-phase generator, the phase sequence, three-phase circuit connection and voltage relationship, power in three-phase circuit, per phase circuit analysis, and unbalanced system analysis. So we said that the three-phase system is a combination of three single-phase systems. So this is the voltage expression of the three-phase system, VA, VB, VC. And those three voltages are shifted by 120 degrees or 2 pi over 3. So as advantages of the three-phase system, three-phase motors, generators are simpler and cheaper and more efficient than a single phase. So three-phase system machine, for example, can carry more power compared with a single phase machine with the same size. So if we have two machines with the same size, the three-phase machine can carry more power compared to a single phase machine. Also, the three-phase transmission line can deliver more power, and you have seen that all the transmission lines and the electric networks are in three-phase. Also, the three-phase more reliable, so it's more confident. Also, this point, which is very, very important for AC machines, unfortunately, we couldn't do them this year. The production of revolving field, rotating field, magnetic field, that's necessary for motor operation. This point is essential for AC machines, that we need a rotating magnetic field. So the three-phase system is basically composed of three single-phase systems that operate in sequence and shifted by 120 degrees. So those are the voltages shifted by 220 degrees, which is 2 pi over 3. Now, the second point we have seen, considering the magnet with rotate with a constant speed and three winding coil are placed shifted by 120 degrees. So this representation is a simple design of three-phase generator, where we have three coils shifted by 120 degrees, and we have a magnet that rotates here in the middle. So the induced voltage in the winding, so according to Faraday's law, we said in Faraday's law, when we have, for example, a time change in flux, that can induce a voltage in a coil. So this magnet have a flux. So when we rotate this magnet, so the flux of this magnet is variable. It's not constant, because it changes according to the position of the magnet. So each time it will induce a voltage in those coils. So the induced voltage in winding have the same voltage effective value. However, the peak occur in different moments. So you can see here in this motion, that according to the position of those magnets, which is rotating, the peak. So the peak of the voltage each time appears with a phase, according to the position of the magnet. So it will be maximum when the magnet is aligned with an axis. For example, if the magnet aligned with A here, so A, the peak of A will appear. If the magnet is aligned with B, the peak of B will appear. If the magnet is aligned with C, the peak of C will appear. So those three induced voltages are shifted by 120 degrees due to the design of this generator, and have the same effective value of the voltage, but the peak change each time. So the peak appears each 120 degrees, and those are the shape of three-phase voltages. The phase sequence system has an important. The three-phase system has this property which called the phase sequence. So the phase sequence is the order of the voltages. So it's the order which three voltages become positive successively. The phase sequence determines the direction of the rotation of three-phase motors and generators. So by taking this three-phase system, we're going to have two phase sequences. So if we take this, for example, in this three-phase system, if we take this direction V, B, C, VA, VB, VC, we have the first phase sequence, which H is A, B, C, and we have the other. If we took the other direction, we have VA, VC, VB. So we have two phase sequence. It doesn't matter which axis we are going to take. So, for example, here, if we take B is the first one, so this phase sequence is, for example, is BCA, which is the same as ABC, BCA or CAB. So this is the phase sequence. ABC can be described also as BCA if we start from B, and can be described as CAB if we start from C. So ABC or BCA or CAB. Now, when we shift between two axes, like this, we're going to pass to the other phase sequence. So we have A, C, B. Or if we start with this one, it's CBA. And if we start with this one, it will be BAC. So the ACB sequence can be described also as CBA or BAC. Okay. Okay, we didn't talk yet about the Phasor diagram, but it's a Phasor diagram, of course. Here in our course, here we have described an example to clarify the phase sequence by when we have a disk. For example, you can see here we have a disk. When we have a disk and we stand here, we have a disk and we stand here in this here, for example. If we stand here and we rotate the disk in this direction, for example, counterclockwise. So here, when we stand here and we see this disk is rotating in this direction, so we are going to see A, then C, then B, which is for example, the phase or the second phase sequence. And if we rotate this disk in the other direction, we are going to see A, B, C. So this is the meaning of the phase sequence. We can call this positive direction and we can call this negative direction, but in fact, in rotation, I think we say clockwise or counterclockwise. So if the disk rotates counterclockwise, the letter appears in sequence ABC. So it's positive. It can be described also as BCA or CAB. If we rotate it to the other direction, we are going to pass to the other phase sequence. Okay. Okay, I'm seeing a lot of questions. Okay. 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 About the phases, the phase in phase sequence. Okay, I'm gonna repeat. Manage. Okay. So here, what I'm going to say. Okay, we are talking here about here we didn't mention the angle or something like this. Just the order of, we are talking about the order of phases. In the next slide, we're gonna see the direction of what is the effect exactly of the phase sequence. Here we said, since we have three phases, when we represent them by this Phasor diagram, for example, if we take this direction, so this one is the vice versa of this one. If we take this direction, so the sequence is A, B, C. If we take this direction, you can say that the angle is negative. Manish. If we take this direction, the sequence is V, C, V, A, C, B. That's it. So we said this phase sequence, the first one, so let's take it as the positive direction. The first one is VBC. Also, it can be taken as BCA, and it can be taken as CAB. While the other sequence, which appears here, is ACB. It can be taken as VCB or ACB or CBA or BAC. So where is the difference? The difference here when we are going to determine the line and the phase voltages. For example, here. If we wanna add for example, if we're gonna add the A to B, for example, so we can move B to this direction, and this vector is VA plus VB in this phase sequence. While, for example, here this vector is VA plus VC, not plus VB. You can see, for example, they are in the same place, but they are different. Okay. I'm going to move to the next slide. It will be more clear. Okay. Now, the three-phase system. Three-phase system can have also a four-wire. Okay, the balanced system. Okay. The natural, which is this fourth wire, with the handle, the sum of the three currents, EA, EB, AC. So if we have a balanced system, this sum will be equal to 0. So what are the conditions of, I will repeat them, what are the conditions of three-phase balanced system? Firstly, we have the same values of the voltage. We have the same effective values or peak values of the three voltages, and we have the same load for sure in the other side. Also, the shifting must be 120 degrees between each two phases. So those are the conditions of three-phase balanced systems. So if one of these conditions So if the shifting is not 120 degrees for between two phases, or the voltage values are different, okay, or we connect with different loads for each phase, it will of course cause a difference in the currents. So that system is unbalanced system. And when we have unbalanced systems, we're going to have a current here in the neutral. Okay, so the conditions basically of the three-phase balanced systems, we must have the same voltages of each phase, and the shifting must be 120 degrees. If one of these conditions is not achieved, the system will be unbalanced system. Now let's determine the voltages when we have let's determine the voltages, the line and the phase voltages when we have three-phase balanced system. So here we call this is the source. We call the voltage between the phase and neutral. We can call it phase to neutral or phase to ground. Okay. So saying ground is easier than saying neutral. Okay. So this voltage, for example, AN or BN or CN are phase voltages. We call them phase voltage or phase to ground or phase to neutral. Okay. While we call this voltage between the phase and the other phase, the voltage here, for example, this voltage VAB, VAC, or VCA, we can call them phase to phase voltage, phase to phase. We can call them line voltage. We can call them also line to line. It's depend on the reference and the books. Some books call them line to line. Some books call them phase to phase. Some books call them line voltage. But in order to do not get confused, let's use this. Let's say phase to ground or phase to neutral or phase voltage, and we say phase to phase or line voltage. Okay. So here we have VAN, VBN, VCN. So in order to determine those voltages VAB, VCA, and VAC. Okay. Okay. Okay, so to determine those voltages, what we are going to do, for example, let's see here, VAB, for example, equals to what? VAB here equals to, so vector, of course, VAB equals to what? Equals to VAN minus VBN. VAN minus VBN. VAC equals to what? This one equals to VBN minus VCN. VBN minus VCN. And we have VCA. Why VCA here? Because we have to respect the phase sequence AB. We have to respect the phase sequence AB, BC, CA. Okay. This one is sorry. This one is BC. It's a mistake. Sorry. This one is BC, not Okay, so here it's correct, yeah, it's BC. So this one is BC. So let's repeat again. So to determine the phase-to-phase voltages, so we have VAB equals to VAN A, which means A phase to neutral or to ground, minus VBN, then VBC, this one, which is VBC, equals to VBC equals what? VBN minus VCN, VBN minus VCN, and VCA here, so it's in the other direction. Why? Because we have to respect the phase sequence. So we cannot, it cannot be like this. For example, VAC. It must be VCA, because from C we return to A. It's a circle. Okay. From C we go back again to A. From C to A. So it's like a circle. So we write VCA, which means we have to respect the phase sequence. VCA equals to what? Equals to VCA equals to what? Equals to VCN minus VCN minus VA. Sorry. Yes, VCN minus VAN. Okay, it's VCN minus VAN, and we have done this before in the class. So let's see what we have done in the class. Okay. So here VBA equals to VAN minus VBA. VBC equals to VBN minus VCN, and VCA equals to VCN minus VAN. So here, always we take those letters A, B, BC, C, A. And this is the phasor diagram. So according to this expression here, let's change the color. Okay, it's so thick. Okay, according to this expression, we can draw the phasor diagram of the three-phase system. So firstly, we start by drawing the first three phase, which are VAN, VBN, VCN. Okay, let's draw them in using this board. Okay, so we have three phase, so like this, almost shifted by 120 degrees. Okay, so those are the three phase, which are VAN, VBN, and VCN. VAN, VBN, and VCN. And those vectors equals to what? So VAB. So VAB equals to what? Equals to VAN minus VBN. So this is VAN. This is VBN. Okay. So in order to represent VAB, what we are going to do. Okay. So this is VBN, but here we have VAN minus VBN. So we draw minus VBN. Let's choose another color. We draw minus VBN like this. This one is minus VBN, minus VBN. Then we can draw the summation of VAN with minus VBN. So we move minus VBN here. It's the same. Okay, we move it here. So this is minus VBN also. Then we can add draw the summation starting from the beginning of the first one and the end of the second one. Okay, like this. So this is VAB, and we can see that those face-to-face voltage are shifted by 30 degrees from the phase voltages, and we can draw the others in similar ways. So, but what we need here, which is important here, we need this triangle. We need this triangle to determine the relationship between VAB and VAN or VBN. What is the relationship between this voltage and this voltage? We know, of course, it's square root of 3, but we need to prove it. Okay, so when we take this triangle here, you can see here this triangle, which is the same as this one. So if we see this triangle, we can see that VAB equals to what? So the angle is 13, also is 13. We can see that VAB equals to VAN cosine 13 plus VBN cosine 13. So this length is VAN cosine 30, sorry. So this length also is VBN cosine 30. So it's equals to 2V cosine 30 and equals to square root of 3, because cosine of 30 is square root of 3 over 2. So this is the relationship between the line and the phase voltage. But this, when we have, of course, when we have a delta connections. Okay, let's continue. So these were for the delta connection system. So you know that in the three-phase system we have two types of connections. We have we have delta Y and delta connection. So sorry, what I'm saying. So this is for Y connection. We call it Y, or yes, it's Y or the star, not delta. Okay, we call it star or Y connection. So this one for the Y or star connection, because it has the shape of star. So this is for Y connection. In Y connection, we have two voltages. We can see that we have two voltages, which are the phase voltage and the phase-to-phase voltage, while we have a single current. We can call it phase or line current. So the line current and the phase current are the same thing. In Y connection, line current equals to the phase current, same current. Okay. While for so this is the representation. We said we need this triangle to determine those relationships. Okay. While in delta connection, we have a single voltage, which is the phase voltage, and it can be called also line voltage, because are the same thing. While we have we have different currents. We have this current in the line, and we have another current in the phase. What is the phase current? Is the current of each one of these, EAB, And here we do the Phasor diagram with currents, not with voltages. So here we have, using this relationship of currents, we are going to do the Phasor diagram in the same way, and we are going to prove that the relationship of voltage and current in delta connection is vice versa from the Y connection. VL equals to V phase, line or phase, and the line current is equal to root of 3 of the phase current. So all of this you are not required to each time prove this relationship. We are going to take it directly. For Y connection, this is the relationship. For delta connection, this is the relationship. Now let's see the transformation from Y to delta. And we need this transformation, for example, when we have a load. So here, this is a delta connected load, and this one is a Y connected load. When we are gonna to, for example, here, when we gonna measure the load between the point A and the point B. Okay, between A and B. We want to measure the load. Here, for example, between A and B, so between A and B, we have this one and this one. ZY, we have two ZY. We have two loads or two resistances, for example, connected in series. So this is the load when we have a Y connection. While here we have what? We have this one in parallel to those two. So this circuit, when we simplified it, it's become like this. It's become Z delta, and here we have two Z delta in parallel. Okay, so ZAB equals to what? Equals to Z delta in parallel with 2 Z delta. Okay, and it's become what? It's become 2 Z delta square over 3 Z delta, and equals to what? Equals to 2 Z delta over 3. So when we take ZAB from here and from here, we can deduce that 2 ZY equals to 2 over 3 Z delta, which means that ZY equals to Z delta over 3. Is it clear, or you want me to repeat it? You didn't get it. How can the 2 delta be in series? Okay. Okay, I'm going to repeat it. Because we need it. This one, we need it for later. We have there is something I have add more details in this course compared to the one done before the pandemic, which is the per phase analysis, per phase circuit analysis, which is the way to solve all the problems of the 3-phase when we have a balanced system. So let's repeat it. Okay. So here we have a delta connected circuit load, and here we have a Y connected load. So we want to take the load between the point A and B. Okay. So if we take A and B, this one, it will not be taken. Okay. For example, let's see, if we have connected here an ohm meter to measure the load. For example, we connect a multimeter or a ohmmeter to measure the load. So it will take those two. This one is not connected. It will not be taken. Okay. It will not be taken. But here, if we connect, for example, a multimeter here, a multimeter, it will take what? It will take this point and this point. Okay, so here, all of them are connected. It's when we simplified it, it will be like this. This one in parallel to those two. Okay, A and B. While here, it will take only two in series. A and B. Is it clear or not? Yes, it's correct. Yes, Asif. But what about the current in the now? It's okay. The third one is open. It does not have a current in this case. In this case, it does not have current because it's open. Okay. It's open. It does not have a current. Okay. It's open. Yeah. Let's continue. So here, by those calculation, ZAB equals to ZY plus ZY, which is 2ZY. While here we have Z delta in parallel with 2Z delta. And this equals to what? Equals to Z delta times 2Z delta and over Z delta plus 2Z delta, which equals to what? Z delta square, 2Z delta square over 3Z delta, and equals to what? Equals to 2Z delta over 3. So 2Z delta over 3 equals to 2ZY. So ZY equals to Z delta over 3, which means that the delta connection can handle more load compared with if we have the same system and we connect it in delta, this system will support more current compared because it can handle more load, because here Z delta means that the Z delta is 3 times ZY. Okay, so the delta connection can handle this. One of the advantages of, in some applications, this one of the advantages of the delta connection over the Y connection. But it's depend. In such application, we need, for example, when we need the network point, we have to connect it in Y connection. Okay. Okay, I consider this point is clear. Let's move to the next point. Now, this is an important point, which is the power in the three-phase circuit. Here we have multiple loads. We said before in the first part of the single phase, when we have multiple loads, the active power of the global load is the sum of all active powers. Also, the reactive powers, of course. So here, starting by the Y connection system. So we have phase voltage, and we have the line voltage, and we have the line current, which is the same as the phase current. So when we take a single load, the power of this the power of this single load equals to what? Equals to the voltage, P equals to the V phase, because V phase is the voltage across the load, not the line voltage. The voltage across this load is V phase times what? Times the current, which is the same as V phase or V line. So let's write it V phase, cosine phi or delta. So when we take single load, so when we have three of these, because they are identical, we have the voltage is what? The power is what? The power is 3 V phase, I phase, cosine phi or delta, and Q, the reactive power, equals to 3 V phase, I phase, sine phi or delta. But when we replace the voltage, the phase voltage, which is with the line voltage, V line equals to, in the Y connection, we are talking about the Y connection. In the Y connection, V line equals to square root of 3 V phase, while the line current is the same as the phase current. So when we replace, so V line equals to what? V phase equals to what? Equals to V line over square root of 3. So when we replace this one here, we get what? We get V line multiplied by square root of 3, because 3 over square root of 3 equals to square root of 3. So expression in terms of line voltage and line current, it will be written as square root of 3 V line, I line, cosine phi or delta. This is for the Y connection. Okay, phi here it's the shift angle between the voltage and the current. Of course, at the beginning I was using phi, then I changed it to theta in the next chapters. Okay, so here it's still phi. It's phi or theta. It's the same thing. Okay, is the shifting of is the shifting angle between the voltage and the current. So this for the Y connected system. However, when we have delta, okay, in delta connection system we have V phase. So this voltage V phase is the same as the voltage across the load. V phase here is the voltage between A and B. It's the same as from this point to this point, or from this point to this point. It's the same voltage, of course. While the current here, the line current, it's not the same. The line current, it will get divided here in this node. It's in this node. So the power is 3 V phase, the voltage across the load, times the current flowing through the load, which is the I phase, cosine phi or delta, phi or theta. Also Q is 3 V phase times I phase, sine phi or theta. Here in the delta connection, it's vice versa to the previous case. The voltage, the line voltage equals to the phase voltage, while the line current equals to square root of 3 phase current. So if we replace the phase current equals to what? Equals to line current over square root of 3, it will lead us to the same expression. So here P equals to square root of 3 V line, I line, cosine phi or theta, and Q is square root of 3 V line, I line, sine square root of sine theta or phi, and S of course is V line times I line times square root of 3. So whatever we have Y connection or delta connection. when we work with, when we use line, when we use phase and phase voltage and phase current, the power is 3 V phase I phase cosine theta. When we use line voltage and current, it's square root of 3 square root of 3 V line I line cosine phi. Whatever, we have a Y connection or a delta connection, because in each system of this, one of them the current is the same, the other the voltage is the same. So it will lead us to the same expression. So when we use phase quantities, we have 3 V phase I phase. When we use line quantities, we have square root of 3 V line I line, whatever the system is, Y or delta. Yes, in sometimes you need to do the transformation, of course. Okay, yes, phi is the shift angle, like theta, same thing. Okay, so this is the power of this is the power in the three-phase system. Let's continue. Now let's talk about the power measurement. So the power measurement experimentally of the three-phase system, it can be done by many methods. We have different methods. The first method is the method of the single wattmeter. So this is the three-phase load, for example. Okay. In case of three-phase 4-wire, okay, so we can use this method when the neutral is accessible in the system. Okay. So in three-phase 4-wire system, three-phase but 4-wire, the fourth wire which is the neutral or the ground. In case of three-phase 4-wire balanced system, single-phase wattmeter can be used. So P total, the total power is equal to what? Equals to 3 P1, 3 times the power measured in the first phase. So it's equals to 3 V phase I phase. So the condition of using this method means that it should be balanced system, and the neutral point is accessible. Okay, this is the first method of measuring the power. The second method is the method of 3 wattmeter. This method can be used for balanced or unbalanced system, because here we are each phase we are gonna measure its own power. So here the power, also here the neutral point must be accessible. But here we have a feature here with this method. So the power is equal to what? Equals to P total, P1 plus P2 plus P3. So here we have measured the power of each phase. So if the neutral point is not accessible or the load is delta connected, the voltage coil can be connected to each other. So if the neutral is not accessible, we can connect these points to each other. We said that the wattmeter has a series coil and a parallel coil like this. We can connect those parallel coils to each other as when we don't have a neutral. Okay. So the second method is the method of 3 wattmeters. So we measure each phase independently or separately. Okay. The third method is the method of 2 wattmeters. So this method can be used when the neutral point is not accessible. So here we measure the power between the phase A and phase C, and the power of between the phase A and the phase C, and we can measure the power between the phase B and phase C. Here, the total power equals to what? Equals to P1. Here, we don't have neutral. It's AB and BC. The total power equals to P1 plus P2. And the reactive power, so this method can measure also the reactive power, equals to square root of 3 P1 minus P2. Why? Okay. Why? I give you a quiz that time to I give you a quiz to prove these expressions. Okay. Quiz, try to prove these expressions. Unfortunately, there is a single student who answered me. Okay, in all the promotion, there is a single student who answered me. That time, at the beginning of the pandemic. So this method has a proof. It's not with me now, but I will try to bring it with me next time, inshallah. Okay. So I repeat, there is a single student who who answered me about this for this quiz. Okay, let's continue. Now we have the most important element in this part, or in this chapter, which the method you use to solve the problems of three-phase system, which is the per-phase circuit analysis. What is the per-phase circuit analysis? If the three-phase power system is balanced, of course, the condition here, the system must be a balanced system. It is possible to determine the voltage, the current, the power at various points in the circuit with the per-phase circuit analysis. So here you can see this system. Okay, so when we have this figure show a Y-connected power source connected to a Y-connected load through three-phase transmission line. So we have here a source, three-phase Y-connected source, and we have a Y-connected load. Okay, and this is the transmission line. This is the impedance of the line. This is the impedance of the line. Sometimes it will be, sometimes it can be taken, sometimes it is neglected because it's too small. It's sometimes from problems to problems, sometimes they consider it, sometimes they neglect it. So, in this system, the neutral wire may be inserted with no effect on the system. So the wire, the neutral here, if it's not added, we are going to add it. Okay, we add the wire. Then it is possible to analyze a circuit consisting of one phase and the neutral. Okay, so at the beginning we have a three-phase system, Y connected source with Y connected load. So the first step, we add the neutral. Okay, then we try to analyze. Let's try to analyze a single phase like this. For example, if we apply, if we try to draw a mesh here, for example, from for example A starting from here to this load, then we return by this neutral. Okay. So the equivalent circuit of this one, this is the first phase. Let's change the color to see the second phase. For example, we start from B. This is B. This B, like this, and or no, it's the positive direction. Okay. So the first phase, starting from here, and we return with the neutral. Okay, this is the first one. The second one, starting from here, this is the second one, returning by the neutral. The third one, starting from here and return by the neutral. Okay, so here we can take a single phase. So it's possible to analyze a circuit consisting of one phase and the neutral, and the result of the analysis will be valid for the other two phases. So we work with a single phase. So this is the key of solving the problems of the three-phase system. So we consider it as, of course, the condition here, it must be balanced system where all the phases are identical. Okay, so it must be a balanced system where all the phases are identical. So if they are identical, so we can take one of these phases as a single phase circuit, and we apply the laws and the rules of a single phase circuit, and it will be valid for the other phases. However, if the circuit is delta connected, it must be converted to Y connection in order to simplify our study, and we are going to see an example. Okay. Okay. You want me to repeat this part of the per phase circuit analysis? Okay. So this part is the most important, maybe, in our part of the three phase. And if this part will be included as an exercise, you're going to use this analysis. Okay, I will repeat. Okay. So if power system is balanced, of course it must be balanced. Because why we said balanced? Because the unbalanced system has another method for analysis, and we are not going to take it because we don't have much time. And I give it to you in the additional recitation, if you remember. In the additional recitation, I give it as an extra information, a method how to analyze a circuit when we have unbalanced system. But here, let's consider the system is balanced. So if the system is balanced, it is possible to determine the voltage, current, and power at various points in the circuit with per phase circuit analysis. So the figure here shows a power system, a power source connected to a Y power source connected to Y load through three-phase transmission line. So here you can see the impedance of the transmission lines. Sometimes it is neglected, sometimes it's taken, no problem, it's an impedance. Okay, so this system, when we are going to simplify this system, okay, we can see that this is, firstly we need to add, if we don't have the neutral, we have to add it, because in the balanced system, the presence or the absence of the neutral or the ground does not have an effect on the system, okay, if the system is balanced, of course. So we add it. If it's not added, we add it. We add the neutral line or the wire. So the first phase, this is the first phase source. So we can take this like this. Okay, this is the first load, and we return back from the neutral. This is the first phase. We can take also the second one like this. So starting from here and passing to the load like this, and we return by the neutral. This is the second phase. The third phase starts from here, another color, okay. Start from here, passing through the transmission line, passing through the load, and return by the neutral. So we can see that all of them returned by the neutral. So we can take one of these. We can take either the blue or the green or the red here as a single phase circuit, and we can analyze our system as a single phase using what? Using the rules of the single phase circuits. And I think you are good on this analysis. Okay, we can use simplified law with a single phase circuits, and if the system is delta connected, it must be converted to a Y connection in order to simplify our study. Okay, so let's see an example. Okay, the resistance of the line, it's not always neglected. Okay, the current of the source is the same as one of the load in this simple system, because this one is simple case, but we may have different loads connected in parallel, okay, as we have in the recitation. Also, the line impedance, it's not always neglected. Sometimes in such problems, sometimes it's taken. Okay, so let's see an example, a simplified example, then we see another complicated example. So example number 1, a three-phase source deliver a power of 3000 watt or 3 kilowatt to Y connected resistive load, where the voltage is 550. Find the phase voltage across each branch, the current in each line, and the value of each resistance. So here it's a resistance, okay, it's a resistance. The voltage, the line voltage or the phase-to-phase voltage equals to what? Equals to 550 volts. So the phase voltage equals to what in this system? So when we take okay, so what we said at the beginning we need to add the neutral point. So this is the neutral, okay, like this, and we take a single phase. So the circuit is simplified like this. We have a source, and we have a load, Okay, we have a source like this, and we have a load. So here it's V phase, not V line, because it's single phase. It's V phase. So the current here is the current of the phase, and this is R. So V phase equals to what? Here equals to V line over square root of 3. V line over square root of 3, and it's equals to 550 over square root of 3, and it's 318 volt. So the power dissipated by each resistance, of course, it's the P over 3, because we have the total power is 3000 watt. So the power of each resistance is P over 3, and it's 1000 watt. Now the current here equals to what? Since we don't have in this question, we don't have the resistance value. So if we have the resistance value, we can measure the current V over R, of course. V over R. Here the current of each branch, because it's a resistance, so P equals to S. Cosine theta is 1. It's a very simplified example. So we are going to see this a more complicated example later. So the power is what? Is 1000 over 318. So the current is 3.15 amps, and the resistance V over I equals to 318 over 3.15, which is equal to 101 ohm. So this one is very simple. Let's pass to the next one. Okay, the next one is a good example. Okay, a three-phase power system shown in the figure 17. It consists of an ideal Y connected. So ideal, which means it's a balanced Y connected three-phase generator connected through three-phase transmission line to Y connected load. The transmission line has an impedance of 0.06 plus G 0.12 ohm per phase. Okay, so this one is the line impedance per phase, and the load has an impedance of 12 plus G9 ohm per phase. So can I find the magnitude of the line current, the magnitude of the load's line and phase voltage. So V load, we need the V line, and V phase, the real reactive and apparent power consumed by the load, and the power factor. So since we said firstly, the system must be balanced. So here they say it's an ideal, which means a balanced system. If we don't have a neutral, we have to add it. Okay. So if we have a neutral, we have to add it here. Then if the system is delta connection, it must be transformed into a Y connection. Since here we don't have a delta connection, so we apply directly. Okay, so we take one of these phases. Okay, let's take the first phase. So this is the first phase, like this, and like this. So the phase have what? We have the source, V phase, this one is V phase, passing by the impedance of the line impedance, the ZL, for example, and we have the load here, Z phase. Okay, this is the per phase circuit of this system. Then we are going to work on a single phase. Okay, is it clear? Okay. So yes, we are going to see this example, and next time we see problems. Okay, about those examples. I think this one is good. This method is a good method to apply. Now, okay. So since both the power system is Y connected, it's very simple to construct the per phase circuit. So this is the per phase circuit. Taking a single phase, a transmission line, and load. Okay. Yeah.
Sir, so sorry, but can you repeat, please? Because I lost connection.
From what? I repeat.
The second exercise, not the first one.
Okay, no problem. So let's repeat. Okay. Okay, so we said the three-phase system is shown in figure 17. Constructed by what? It's an ideal, which means balanced. Here they said ideal, they mean balanced. Connected the three-phase generator, Y connected. We have a Y connected source. It's a Y connected source connected through a three-phase transmission line to a Y connected load. So the transmission line here, it's not neglected. The resistance of the transmission line is considered. It's 0.06 plus G 0.12 ohm. And the load has impedance of 12 plus G9 ohm per phase. So firstly, for the per phase circuit analysis, firstly, we need balanced system. The first condition is achieved. The system must be balanced. The second, if we don't have the neutral, we add it, because in the balanced system, the absence or the presence of the neutral, it will not affect the system, okay? Because the current of considered zero in the neutral. Then we take one of these phases. Okay, let's take the first one, starting from here, passing by the transmission line, then passing through the load, then returning with the neutral here. Okay, so when we take this circuit, it will be simplified like this. This is the source. This is the transmission line impedance, ZL, for example. And this is the impedance, the load impedance, Z phase or Z load. So this is the simplified circuit. And we are going to apply the conventional, the traditional expressions or rules of the single phase circuit. Okay. So since the source and the load are Y connected, it's very simple to construct the per phase circuit. Okay, so this is the per phase circuit of this of the previous system presented. So we have the source, we have transmission line, and we have the load. Now the line current flow in the per phase circuit. So the line current equals to what? So the line current equals to the voltage. Of course, the line current equals to what? Here, because it's a Y-connected system, the line current is the same as the phase current, okay? Equals to what? Of course, equals to V over Z. Z total, the Z of the line plus the Z of the load, okay? So the source current here, the line current here is the source current, equals to V over Z line plus Z load. The phase current is 120 over 0.06 plus G 0.12 ohm plus 12 plus G 9 ohm. Then the line voltage, the line current equals to what? By changing from rectangular to polar writing. So the current equals to what? The magnitude of the current is 7.94. The magnitude of the current is 7.94. So here we have applied a simple rules of circuit analysis. Okay. Okay. So not always take the given voltage. You have to see if they give you the line or the phase voltage. Okay. So here in our system here, they give us the phase voltage, but sometimes they maybe give you a line voltage. Okay. You have to see if it's a line or the phase voltage. Okay, because here it's a Y connection. It's very simple. We have another case with delta connection. Okay, so there is no given circuit. It's if there is no given circuit, you must construct it. Okay, question by question. Okay. Okay, so why here 280 is the this one is the line voltage. You see here 280 divided by square root of 3 equals to almost 120. Okay, 208 is the line voltage, while 120 is the phase voltage. the angle of the power is the same. We consider them identical. Okay, because each phase is shifted by 120, but the current and the voltage of each phase are shifted by the same angle. Okay. I said for 208, it's the line voltage. Hussein.
Yes, sir. Sir, my question is, to 28 volt. How do we know that it's line voltage in the beginning of the text, the exercise?
Okay, it must be indicated. Maybe here it's not indicated because it's indicated in the figure.
Yes, in the circuit.
It must be indicated, which is it's a line or phase voltage. It must be given. Okay.
Okay, thank you, sir.
Okay, it must be given in the circuit or in the data or whatever. Okay. Here, for example, it's clear that V line is okay. It must be given. هذه ما فيهاش. Okay. Now it must be given. Okay. So they give it to you a way or another way. Maybe in the data, maybe in the circuit. Okay. So okay, let's. So here we have done a simplified calculation. Because the phase voltage here is 120 over the impedance. So if we don't have, for example, if the line impedance is neglected, we use directly the impedance of the load. Then the current is the magnitude of the current is 7.94. Now the phase voltage across the load. Okay. This voltage is the product of the phase impedance and the phase current. So if, for example, if we don't have this transmission line, if the transmission line is neglected in this case, the voltage is the same. The voltage of the source across is the same as the voltage across the load. But this transmission line, it will cause a voltage drop. Okay, so we take this voltage drop from the voltage. This voltage drop will be taken from the phase voltage. Okay, so the voltage across the load equals to the current of the load multiplied by the impedance of the load, and it equals to what? Equals to 119. So it's less a bit. So it's less a bit from the voltage of. It's less a bit from the voltage of the source, because we have a voltage drop due to the transmission line. The magnitude. Okay. Now the magnitude of the load line voltage. So the line voltage of the load, not the phase, not the voltage across the load. The line voltage of the load is of the global load here. The line voltage of the global load, يعني three-phase load, is what? Okay, جماعة, we are working on a single phase, but we don't forget that we have a three-phase system. Okay, so the magnitude of the line of the load line voltage VL equals to square root of 3 and equals to 206.3. So the real power consumed by the load equals to what? Okay, we said that if we use phase voltage and phase current, we put 3. And if we work with line voltage and line current, we put square root of 3. So the load power is 3 times V phase times I phase times cosine. Cosine what? Cosine the angle of the current, of course. Okay. then the power is given with this expression. Also, the reactive power can be measured in the same way. Also, the apparent power can be measured in similar way. Also, the load power factor can be measured in similar way, which is cosine of theta. Okay. Okay, we don't have. Yes, can we use voltage? Can we use voltage divider rule? Here we have a single load, but we have if we have more than one load, we can use the voltage. But maybe we maybe use the current divider. Okay. We have another example, the same example, but with the delta connected load. I think we don't have time. We still have 10 minutes. Okay, let's try to do it quickly. Okay. Okay. So. Sorry. Okay. So the example number 3 repeats the same previous example with delta connected load. We can see that this one is Y connected load. So the load per phase is 12 plus G9. Here, delta connected load they conserve the same load per phase. Okay. So in this case, since the load of this power system is delta connected, it must be converted to an equivalent Y connection. So the phase impedance of the delta connected load is 12 plus G9 ohms. So the equivalent phase impedance of the corresponding Y form. So firstly, we said it must be converted to Y connection. The relationship between ZY and Z delta. So ZY equals to Z delta over 3. So we are going to convert this system into what? Into an equivalent Y connection system. So it will be connected like this. This is the first phase. So it must be connected like this. Okay. How? Okay. For example, like this. Like this. We have the first load. First load like this, and the second load like this. Okay, and the third load like this. So it must be converted into equivalent Y connected system. Then we add, as we said before, we add the neutral. This is the neutral point. So we connect it to the neutral of the source. The relationship between the Y and delta connection, we have seen it in the transformation. ZY equals to Z delta over 3. So we divide this per phase impedance by 3. Okay. Okay, so here the angle. Okay, the angle must be, it should be negative, not positive normally. Okay, let's continue and we are gonna check it next time. Okay, so, okay, zy equals to 3 times, we said 3 delta, z, the impedance in delta connection equals to what? Equals to 3 times zy. So the impedance will be divided by 3. And when we represent that equivalent delta connection equivalent, it's not real, it's equivalent delta connection, we are going to take the per phase circuit, for example, like this starting from this phase, passing by the transmission line, then passing by the load, then we return by this through the neutral. So this is the direction. Okay, and this is the equivalent, the per phase circuit. First we convert it from delta to y, then we add the neutral, then we take a single phase. After that, the calculation will be the same. But here, be careful, the value of the load has been changed per phase. So the current of the line equals to the current of the line equals to the voltage over the line impedance plus the load impedance. Then the phase voltage on the equivalent y is the voltage across one phase. Okay, then the voltage of the load equals to what? Equals to the current multiplied by what? Multiplied by the current of the load multiplied by the impedance of the load. However, the original load was delta. It's not, the original load was delta. It's not y. So this is an equivalent system. So this is the voltage, the phase voltage across the load. In what? In the y equivalent system. But in the original system, in the delta connection, in the delta connected system, it must be multiplied by square root of 3. Then we can calculate the power in similar way. Next time, inshallah, we're gonna have this problem, which have the 2 loads, so they are connected in parallel, and we have this problem also, which have 2 loads also, they are connected in parallel. Okay, and we try to solve them. We still have another. Okay. So the problem of the angle, since because I didn't have, I have so much time, I have taken that solution as it is from the book, but I will gonna check it inshallah next time, because I'm trying to work quickly these days. We have another point. We have another point called the one-line diagram. We are going to see it inshallah next time. The one-line diagram, what does it mean? One-line diagram. And the last point in this chapter is the unbalanced 3-phase load. This point is will not gonna taken this year at least. I give it to you in the additional recitation. So it's for extra information, because we have a different method to deal with unbalanced load. And for me, I see it's complicated for you. Maybe for those who are interested with the power engineering, maybe need it, because the unbalanced system exist in the real power system. Okay. I think I'm gonna stop here. Inshallah, Monday morning, I will check my schedule also, and we try to have a session. At least we do a recitation for for this chapter.